All right. So, in our upcoming reminders and announcements section, there is a mastering due tonight. There's a group quiz next Wednesday. And then these are the upcoming science seminars I know for sure as of right now. So there's one next Tuesday, and then there's one in February, March, and April, all 11 a.m. in here. Those are all specifically chemistry seminars. I'm waiting to hear back from biology and animal science as to when their seminars are going to be this semester. If for some reason you are unable to attend any seminar I offer this semester, your option is to email me and I will give you an alternative assignment. It'll be a 15-20-minute video that you watch and then summarize. Because I know 11 a.m. is a tricky time for a lot of people because there's meetings and clubs and work and whatnot. So if there's no time that you can make one of these seminars, email me and I will give you an alternative assignment to do so that everybody has the equal opportunity to get the extra credit if they want. Questions on that?
So the Temple Grandin thing, that's a go?
That's the 28th. Mm-hmm. Mm-hmm. All right, so where we left off last time, we were considering this reaction. So we want to know the rate of appearance of oxygen. So using what we talked about on Wednesday, right, that would be correct, where's the change in oxygen concentration over the change in whatever time period we're looking at. We also want to be able to define the rates of the nitric oxide appearance and the nitric dioxide disappearance relative to oxygen. We want to know how they all are interrelated, right? If one's appearing, one's disappearing, how fast are they related? So let's think about this in terms of kind of a word question. All right, so from this chemical reaction, right, from the balanced chemical equation, right, that'd be writing it out in terms of words. 2 moles of nitrogen dioxide produces 2 moles of nitric oxide and 1 mole of oxygen, right? That's if I rewrote this equation using words. True? Right? 2 makes 2 and 1. Okay. So, right, just like we just said, if that's true, then we have to figure out how is this oxygen rate related to the NO2 and the NO, right? Because if I make 1 mole of this, I make 2 moles of that, and I make 2 moles of that. Right, just restating it. So let's say if I make 100 moles of oxygen, how many moles of NO would I produce? 200. Which means if I want them to be equivalent, I have to make half as much NO as oxygen. I want the rates to be equal. I want them to be, so I can put equal signs in between them. Which means the rate of NO has to be half as fast as oxygen. Right? So if you're thinking, if you make 100 moles of oxygen, you're going to make twice as much NO. But I want the rates to be the same, which means I have to slow down the NO by half for them to both make 100. Yeah, okay. Which means that would be its rate. The rate of NO production would be half the change of NO over change in time. For it to be equal to, for those to be the same, I have to slow down the NO by half. Because if I left it alone, it'd be making twice as much as the oxygen. And I want them to be the same speed. So I speed down this one by half. And now they're both making 100 moles. So then let's say I want to equal this guy's rate. Will it be as fast as oxygen, or will it be half as fast as oxygen? It has to be half as fast, right? Because it has the same stoichiometric coefficient of 2. So if I put in, I need to put in half as much for the rates to be equal. And why do I have that negative sign? It's disappearing, and I can't have a negative rate. So I have to have a negative rate to make a positive rate. I'm writing kind of small today. There we go. Okay. So how are these fractions related to my stoichiometric coefficients? Oh, question. Ask away.
So you can multiply, like just say, nitric oxide or whatever. You can multiply that by 1/2 without multiplying the whole equation by 1/2 then? Does that make sense?
No.
So in order to get the 2NO equal to O2, the rates, I guess, you can just multiply the 2 by 1/2 without multiplying the oxygen by 1/2.
These are the lowest common denominators, right? So the other way I could write it would be 1, 2, like that would be equivalent. But I'm saying for every oxygen I put in, I have to slow down this guy by half for them to be equal.
Okay.
Right. So that, which means we have a general form we can use every time. All right, so here's my general form for rate equations. Is that if I have a reaction of some amount of A and some amount of B making some amount of C and some amount of D, you take 1 over the stoichiometric coefficient, and that's how those rates will be related. Making note of these guys have this negative sign, right? Because they are on the reactants side.
brackets mean concentration?
They do, mm-hmm, yeah. Yeah, so we're going to start seeing that symbol now, where brackets mean concentration, specifically molarity. It's a shorthand. So that's a new topic. So what are we going to do next? Some example problems. Perfect. So what we're going to do is we're going to give the relative rates of appearance and disappearance for the following reactions using our snazzy new equation. All right, so let's do this oxygen. So I have 2 ozones making 3 oxygens. Let's see, I guess in order to make it match kind of our example up here, we'll do the products first. So what is the fraction that goes with oxygen? Very tricky, very good. For those to be equal, what is the fraction that goes with the ozone? What sign does the 1/2 get? Yeah, negative 1/2. Which means I have to slow down the oxygen by 1/3 to make it equal to slowing down the ozone by 1/2. So now they're equal. All right, why don't you guys try the second one? Equally tricky. Now there's 3 things. Baby steps. Everybody get something that looks like that? Okay. And it is not the David Hasselhoff molecule. It is similar, but not the exact one. All right, so that's great. But why don't we put some numbers to it, and maybe that'll help solidify the thought process. So here is my table of data that I collected, where I watched the appearance of molecule B over time. And at time 0, there's no B, right? Because it's the start of the reaction. There's nothing going on. After 10 minutes, I guess, yeah, it must be in minutes. After 10 minutes, we see this much B appear. 20 minutes, 30 minutes, 40 minutes. So far, so good. It's just a table of data. So the first thing I want to ask is, what is my rate equation based on A and B? So I want to do just like we did. I want to have delta A equal delta B, right? So I want to have, how is the rate of change related? What am I missing from my A? If this is true, right? I missed my negative sign. So then what's the fraction that goes with B? 1/2. Right? So the rate of change of A is related to the change of B through this equation. Well, what I need to do in order to answer this part, the rate of change for A, is I need to figure out the rate of change for B's. Right? Because I collected B data. So what we want to do is we are going to find the average rate over a period of time. So if you don't have your calculators out, go ahead and fish them out, because we'll need them. right. So we can't find the rate of B at time 0 because we don't have enough data yet. For this one, I'm going to look at the change in concentration of B, which was 0.326 minus 0 over 10 minutes, right? 10 minus 0. I didn't leave myself very much space in those little boxes. So that should come out to be, so 0.326. What would be the units of this rate? Per minute, because I just picked minutes, but yeah. It could be per second, right? It's concentration over time. All right, so then now I want to figure out the rate for this next step. So I'm going to do the final. Right, so I'm just taking my new concentration minus my old one over the change in time. That should come out to be 0.0246. Okay, why don't you take 2 minutes and do the last two concentrations. Very tricky subtractions.
Do you not multiply times 1/2?
Oh, no, that's where you can go. That's only if I want to figure out how it's related to A.
Oh, okay.
This is where chapter 13 is tricky about those kind of
I
things.
thought we were finding, are we doing the second question today?
We're working up to the second question.
Oh, okay.
We're going to do this stuff, and then I'll work our way over here. Right, so those are just my rates of B's that I experimentally determined. But now I want to answer part 2 over here. Find the rate of change for A for, which time block did I pick? 10 to 20? So this time block. So I want to figure out right, because I already know delta B, because I just found it over here. And how A is related to B is that A is 1/2 as fast as B. So you just plug it in. Lots of blank stares. Because it's so obvious? No? No, maybe not. Right, so in this table over here, we figured out all the delta B's. So I just plugged in my delta B into my equation. Right, because I'm just using this equation. So this is going to be a chapter that you're going to have to do a lot of practice problems on because it's not necessarily as intuitive as other stuff we've done. It's going to require a lot of sitting down and crunching some numbers for it to make sense. Or coming by my office. All right, so now the last part is I want to know just the instantaneous rate when concentration of B is 0.075 molar. So this is what we were looking at in the graph maybe Monday when we were talking about based on the curve, how do you know what points to pick around the instantaneous one? You can pick any 2 points you want, but I experimentally only determined 5 points So I want to know the instantaneous rate at this concentration. So I need to pick the point above it and the point below it, right? Because those are the only two data points I have. Right, so the point above it and the point below it. How big of a time span is that now? I heard someone whisper it, 20 minutes. So instantaneous rate is that. So these are average rates. So I'm looking over a span of time. An instantaneous rate is for one concentration where you pick up concentration on either side of the concentration you're interested in. It is, but it's considered instantaneous because you were looking at one concentration. The terminology is a little funky. So how about we do some more practice? Because everybody looks a little blown away. All right, let's try this problem. Doesn't have a table of data in it. It should be a little more straightforward. All right, so now I have nitrogen reacting with 3 hydrogens to make 2 ammonias. First thing I want is the relative rates. So I want the rate equal to rate equal to rate equal. That's what I'm asking for. So how about we start off with nitrogen. All right, so if that's my nitrogen, does it have a fraction associated with it? Does it have a sign associated with it? Yes, it needs to be a negative. All right. How about hydrogen? What does hydrogen need in this equation? Needs a negative 1/3. All right, so then what does my ammonia need? Positive 1/2, yeah. Everybody see our crazy methodical method? All right, so experimentally, I went ahead and determined the rate of the disappearance of hydrogen. And I determined that rate is 4.5 times 10 to the negative 4th molarity per minute. I want to find these other rates. So let's do this first. Right, so just taking a little section of that equation. You're going to plug this number in just like you would for x. Like this whole thing is a variable. That helps you think about it. The whole fraction is a variable that can be substituted for. Make a little more visual sense. I have this equation equal to negative 1/3 that rate, but I know that rate, so I just need to plug it in.
Do they have to be positive for that? Do the two negatives cancel out or not?
No. So what does that turn to be? Good. Okay, so why don't you go ahead and solve for the other one using the same. You could either use your new answer or you could use this concentration or this rate. Figure out what the rate of appearance of the ammonia is. I'll work up here. That's totally not right. I mean, that's true. No, scratch that, exactly what I want. Rewrite it over here. Everybody get something like that? 3 times 10 to the 4th? Yes, ma'am.
Why is it that you have a negative on both sides of you have your negative changes into over t equals negative 1.5? Isn't it disappearing since it's going to be one negative sign?
Both would be correct. So this negative sign is telling me that it is disappearing. And so you,
have a negative sign on the other side.
yeah, you can cancel both. You can leave them both there. The negative sign is telling me direction.
But if you take both of them away, wouldn't that tell you that into is appearing?
No. The negative sign to me tells me the direction of it, and so they don't necessarily cancel out. Right? So this negative is telling me that it's disappearing. This negative sign tells me that it's a disappearing rate. So both would be fine. If you would prefer to write negative, this equals a positive number, because that tells you direction, that would be fine also. I think whichever method makes more sense to you, that would be acceptable. We feel pretty confident about plugging it in, writing the equations and then plugging it in? Pretty confident? Okay. So the question is, why bother looking at all this kind of information? All right, so one way to study the effect of reaction concentrations on rate is to determine how initial rates are affected by changing concentrations. That seems a little redundant, right? I pretty much said the same thing 2 different ways. So what do I mean by initial rate? This initial rate. So initial rate is considered the time at like time 0 when you first start. You know exactly how much reactant you put in there, and there should be 0 product because the reaction just started. So the initial rate is time 0 to a few minutes in, so that you can watch the disappearance of products and the disappearance of reactants and the appearance of products without worrying about any kind of side reactions going on. So initial rates gives us the most information about how fast the reaction is going to proceed. So let's look at this reaction up here. Right, so now I have 2 moles of N2O5 producing 4 moles of nitrogen dioxide and 1 mole of oxygen. Right? Now, if we wanted to graph it like we had before, right, concentration over here, how fast the reaction proceeds over here. What happens if I add more N2O5? What happens to the rate? It increases. What happens when I go from 0.01 to 0.1? What happened to the rate? It goes up also by a factor of 10. So my concentration went by a factor of 10, my rate went up by a factor of 10. So if I was doing it versus time, it would look like this, right? Like we had before, where the N2O5 is disappearing over time. But a more interesting thing to graph is the rate of the reaction versus concentration. How my concentration of my reactant affects the rate. So we just said from here to here goes up by a factor of 10. What's the relationship between these two concentrations? Right, it doubled. What happened to my rate? Doubled. From here to here, it went by a factor of 4. Factor of 4. So how are these two columns related? Are they directly related or exponentially related? They have to be directly related. So is that going to be a straight line or a curvy line? Straight line going up or down? Up. Right, because you just said experimentally, I go from, I double that. So that's that point. Quadruple, quadruple. Sextuple? Hextuple? Whatever that is. Right, so now I've made a nice straight line. Everybody prefers straight lines. Because now we have a snazzy equation we can use for straight lines, right? Does everybody know the fish symbol in math? It means directly proportional to. You may not have run into it yet. Means that they are directly proportional. As one increases, the other one increases by the same amount. Which means I could write this that would be true. That rate is equal to K times concentration, where K is now a constant that is true all the time. In fact, it has its own name. It's called the rate constant. Any guesses where on my graph I could find K? It is the slope. Look at that. That's why we love graphing. Well, if you don't love graphing, you will love graphing by the end of it, because we graph a lot. Yay, graphing. It's all linear. Nothing crazy. Y equals mx plus b all the time. All right, so now we have a rate constant that is true for every equation. So let's take that for a spin with some math. I'll do that on the back. I didn't leave myself enough space on that one page. Let's say, which problem do I like better? Let's do this one. All right, here's my really complicated equation. So far, so good. A makes B. All right, I go to the lab and I collect a table of data. I do love tables as well. All right, so I collect a table of data. Numbers, rates, concentrations, and rates. I want to know what is K for this given equation. So we're going to use the equation we just discovered. Look at that. Which combination do you want to pick? First one, second, or third one?
Second.
Perfect. Forgot my units. There we go. All right, some very complicated math. We'll do a whole division over here. 106. Oh. How many significant figures do I get in this final problem? And the last tricky question is, what are going to be the units of my rate? I'm in molarity per second over here and molarity over here. What would K have the units of?
1/2.
1/seconds. Or inverse seconds. All right, because if you think about it, over here I have molarity per second, and over here I have molarity. So the only way the units would be equal on each side would be to divide the molarity by seconds. So its units have to be inverse seconds. Feeling confident about that crazy math? Feeling confident? Yeah, okay. It gives us the general form of the rate law. So before we had the general form, I lost my page, of the initial, of relative rates. Oh, there we go. All right, general form of rate equation, which are relative rates. So I'm comparing products and reactants. This is the rate law, which is used for initial rates. What is the difference in these two equations? A few things. In my relative concentration rate equations, I'm comparing appearance of products and disappearance of reactants. Right? I'm comparing how fast each of them are appearing. What am I looking at in my initial rates? The overall rate, and do I need anything about the products? No. Initial rates only look at reactants. And it's because at an initial rate, at time 0 of your reaction, how much product should be in there? 0. So there's no point in having it in there because there's none. We're looking at the initial reaction of how fast those reactants are being used up. We can then figure out later how fast the products are being made. That's easier for us experimentally. You know you put in 10 grams of reactant, and you want to follow that 10 grams disappearing. It's very hard to start measuring at 0 to measure the appearance of some things. Easier to watch stuff disappear and to appear. All right, so here we have the rate. That is in units of typically molarity for some time period. K is our rate constant. And it'll have units of some sort of time period. It'll either be inverse seconds or a few different things it could be. But it'll be measured in time. We have our concentrations of A and B. That's typically going to be molarity. And then we got our crazy exponents. Do X and Y appear anywhere in my given equation? They don't. They are experimentally determined. So unlike the average rates we just looked at, the comparative rates, X and Y can only be determined by doing an experiment and collecting a table of data. And they have the name reaction order. And they can only be determined experimentally. So, in this, actually, let me go back one. In this reaction,
Right?
I have my experimental data.
And
When I doubled this, the rate
doubled.
When I quadrupled this, the rate quadrupled. That's going to tell me my reaction order.
How
When I change the concentration, how the rate
changes. That's where the reaction.
order comes from. So it comes from when we change the concentration, how does the rate of...
Reaction change.
So,
If we need to
determine these x's and y's experimentally, how do we go about doing that? I know it's the question that everybody's considering.
Man, how do we figure that out?
Don't you worry. I'll do it right now. That way I
Don't leave you on a crazy cliff.
cliffhanger for all weekend. I don't want you guys going crazy thinking,
Man, I really wish you would have
told us before class period ended. All right. So the initial rates of reaction
measured with different.
different starting amounts of reactants, just like we did 2 minutes ago, right? We had a table,
Bunch of different concentrations.
measure a bunch of different rates.
So here is my
Go-to reaction, pretty straightforward. Let's say I am measuring something like that.
good rate versus
Versus concentration of A. And before, we had this very nice,
linear line.
right, that was from 2 minutes ago, where if I
Doubled
doubled
the concentration.
the rate doubled, tripled, quadrupled, quadruple. That is
It's 1.
x equals 1. It means that
Whatever I do to the concentration,
is directly shown up in the rate.
right, I doubled the concentration.
I doubled the rate. Multiply by 10, multiply by 10.
That means they are directly related.
So we'll make a little table to keep track of. So when the order is 1, my rate law for this will be
Rate
equals K concentration of A. Raised to the power of 1, but that's implicit.
All right, let's think about
If I was a second order, if I wrote my equation,
equation like this.
right, so if I have rate,
Rate constant.
now if I double the concentration of A, if I start
Started at
3 molar and I went to 6
molar.
instead of just being directly related, they're now to the power of 2, right? It's being squared.
Squared.
I'll make a new little comma over here. So if I
Double A the rate.
doubles, if I double A from
3 to 6.
my rate has now gone,
It was doubled, and
now
now
it's squared of 2.
do I get an exponential curve?
If I raise to the power 3, I go from
If I double
double A, I go from 2, I square 2, I get 4. If I go from doubling and then I raise to the power 3, this should be All right, that was squared. What's 8? What's 2
Cubed.
I already said it, 8. Power of 8. All right. Ooh, I forgot to draw my line. Super crazy curve. All right, what if my power of A is now 0? What happens if I double the concentration of A, if I go from 2 to 4? Okay, what happens when you raise something to the power of 0? 1. So now it's rate equals rate constant.
So nothing happens.
So what would that line look like? If I change the concentration, rate's not affected.
So how would this look?
Oh, okay. Okay. All right, that's where I'll leave it for today. When you come back Monday, we'll do a bunch more practice problems of solving it, graphing it, collecting the data, figuring out how you know what order is what.